Okay, so would you like me to share my presentation, sorry? Okay, so I will share my presentation slides, okay. Okay, thank you for your attention. I'm a Dr. Mazin. I'm a lecturer at Mustansiriya University in Baghdad, Iraq. And I'm one member of CYRIX group at Cardiff University in the UK. My topic of the presentation would be the use of electric vehicles to provide ancillary services of the frequency response for the GP or for the Greater Britain port system. Yes, I have divided my presentation into two parts. So in part one, I will talk a little bit about what is going on in our future port system, and then I will talk a little bit about the services that we could use in order to provide frequency response. So for introduction, in a modernized port system, there would be a big change in the way we consume and produce energy, because we will see thousands of wind turbines would be spread out alongside with the PVs. Intelligent load could be, electric vehicles would be much more appreciated in the future. So it's really all about energize our port system and electrify our load, where the electricity could be produced everywhere and transported in the all directions, not only in one direction, just like the way we used to see in a traditional port system. However, that significant changes in our port system landscape, of course, will not come in an easy way. We will face several adversities, and one of these biggest adversity could be the rapid change in the system of frequency as for the massive penetration of renewables. So what is the grid frequency? The grid frequency is the balance between the power of generation on one side and the power of demand on the other side. So if the both are equal, then the frequency becomes constant and is denoted 50 Hz or 60 Hz depending where you are. Any power mismatch between the power of generation and power of demand will cause the frequency to variate, and that variation in the system frequency is expected to become even higher in the future with the more penetration of renewables, and if we keep on the current arrangements to provide the frequency response. So obviously actions need to be taken in order to provide faster frequency response to the network. Again, here I'm talking about the GP port system, the Great Britain port system, but could be globally talking. There are three elements that we could use in order to provide frequency response to the network. And these elements are the generation based on the generation side, demand side, and energy storage system. Okay, so because my topic is about the providing a frequency response from the energy storage system, so I will talk only about the energy storage system. And I guess for all of the researchers, especially at this area, they know about the how to provide a frequency response based on the generation units on demand side. Within the energy storage system, I'm here specifically talking about the battery energy storage systems. So we could use the characteristics of charging and discharging of batteries in order to stabilize our grid frequency. For example, we could store the surplus electricity when the frequency rises, or we could charge our EV batteries, for example, when the electricity is cheap. And for some circumstances, when the frequency decreased, these batteries could release their power back to the system in order to compensate for the power loss and stabilize the frequency. In the part two of this presentation, I will talk a little bit about the technology that I'm dealing with during my study. So dynamic demand response service, I will talk a little bit about that one. And then I will show you the control algorithm that I've developed, and I name it the DVGS, Dynamic Vehicle Grid Support Control Algorithm, in order to provide dynamic demand response for the GP network. So what is the dynamic demand response? It is a services that is required to stabilize our grid frequency continuously, second by second, 24 hours in a day. And this service could be obtained by several candidates. For example, the electric vehicles, or could be by some thermal units like the heat pumps, fridges, etc. Of course, these services are cost-effective services because what we are doing, basically, we are reducing the dependency on the frequency response from the frequency sensitive generators. And of course, also these services are clean because they do not cause CO2 emissions. So this is the demonstration of the control algorithm that I've developed, the DVGS. In this control algorithm, basically I have combined three control algorithms. The first control algorithm is shown here in block A, which is the control algorithm of the charging EVs to control the state of charge of EVs during the normal operation. In block B, the control algorithm here is the dynamic frequency control algorithm, and I call it the term here dynamic is because I conducted her dynamic relationship between the state of charge of each EV with the frequency, with the grid frequency, and I did that one by assuming two frequency set points, the L frequency and high frequency set points, and these set points were chosen based on the frequency levels at the UK, and is continuously updated based on the state of charge. And the reason of that dynamic relationship is to achieve several factors. For example, to ensure a smooth triggering for the responsive EVs when there is a frequency occurrence. The third control algorithm is shown here in block C, which is the control algorithm of the charging EVs during a critical time, because because here I'm talking about the domestic EVs. So each EV driver must wake up with his EV fully charged by the morning, otherwise will make him maybe upset. So during the critical time, we need to specify a critical time where the EV should be charged deliberately, even if there is a frequency incident. For more information about the detailed model, I recommend you to have a look at my paper cited below the slide, and I think it will come up online just a few weeks later. So I got some collaborative links with National Grid, the system operator in the UK. So they allowed us to use both of their models, the dynamic reduced model and the very detailed model, which they call master model. And by the end, so we integrated our dynamic vehicle grid support control algorithm with their model, and by the end we hope that our work could help National Grid to shape their understanding about the frequency services from the aggregated dynamic vehicle grid support. Okay, so this is the dynamic reduced model of the GP port system, which is at present at National Grid, and is dispatched for the future scenario, 2030 future scenario. So it has 332 zones. I've connected my electric vehicle models at only 11 zones, because these zones are geographic representation for the 11 DNOs of the GP network. And it's worthy to mention here that the number of EVs I got it from a project that Element Energy have accomplished for National Grid. Element Energy, by the way, is the national consultancy in the UK. So here is the results. You see here, this is the grid frequency. I injected here a frequency drop at time 5 seconds, and I measured the grid frequency with and without the dynamic vehicle grid support. It's very obvious here that the dynamic vehicle grid support reduced the frequency drop significantly. On the second figure here, we could see that the power of EVs reduction at different zones after the frequency incident. And the third figure here, this is the power shown by the generators with and without the dynamic vehicle grid support. We can see also here that with using the dynamic vehicle grid support, we have reduced the dependency on the frequency response from the frequency sensitive generators. The last figure is the change of charging power according to several large contingency, which is measured by gigawatt. However, in the UK, the infrequent in-field loss is between 1.5 to 2 gigawatts. So within that range, we could see here that our model has reduced the power of EVs by almost 450 megawatt. So provided 450 megawatts of a frequency response. That's just 2 milliseconds after the incident. In conclusion, the dynamic vehicle grid support control algorithm achieves different factors, because it could contribute in the balancing services in the UK. For example, the dynamic firm frequency response in the UK, and also meet, of course, the renewable policies. It is a cost-effective technology because it is all about the markets. So in the UK, the frequency response has a value in the market. So that's the end of my presentation, and thank you very much. Sure. Sorry, say that again. I didn't catch that. Hello. Yeah, say that again, please. I couldn't get that. Yeah, sure. Okay. Yes, basically we are struggling about the problem of the reduction in the system inertia or the natural torque of our power system, because now we are experiencing a massive integration of renewable energy, and that so we are replacing the synchronous generators with other kind of asynchronous generators, or could be what we call the converter connected generation units, like the PV wind turbines. So that could reduce the system inertia or the natural torque of power system. So that's the motivation of my work when I saw that problem statement, a very important problem statement. So I worked both on the demand side response, and I published paper at ICAE transaction on power system, providing frequency response from thermal loads like the heat pumps. And also, this is my current study, is to also provide frequency response based on the electric vehicles. Hope that answers your question. Yeah, no problem. No problem. Thank you very much.